same guy that use the same equipment, use the same sample to measure multiple times, 10 times, something like that, right? Your variation should be very small, but yet you have variation in real life. It's just like you put a micrometer, you click it there, see? Then after they unscrew it, you check it in again. You always have one division plus minus something that always wrong, always different one, right? Slightly, right? Sometimes pattern you speed it up a little bit. The pump move over, something you would guess, right? You have variations. So that variation there is called repeatability variation, right? Now, next you have another scenario. You have a same sample, same equipment, but different person to measure it. The different person, because your eyeball, or your nature, everybody do something different, right? So you also introduce variation inside there. So that variation, you see, is due to human. Human has a bigger element inside there already, in that sense. So that's called reproducibility. The term, reproducibility. Okay? So these are the two terms that we, in our chart earlier, we say that, right? That's what we are trying to understand, right? Okay? Now, the total variation, right? In the chapter 2, we talk about the additive nature of standard deviations and the variant, right? Standard deviation cannot add, only variance can add, right? Additive. So the total variations, right, of a product, right, is the variations on the product itself and the variations due to the measurement equipment. And the variations due to the measurement equipment itself there, see, you have dialed up the bias, linearity, stability there, see. Then the other two contributing factor there, see, is so-called repeatability and reproducibility. So these two, if you square add together, this is called measurement system variance, right? Or R&R variance. R&R stands for repeatability and reproducibility. So as simple as that. You don't want to write, wow, so many words inside that. So it's R&R. Okay? So now, so the total variations, right? After you take out, dial up the bias, stability problems, and then the linearity problems, if everything all taken out by equation there, by equipment. So what is left is that your true product that's coming from the process, right? In this case here, we say the product and the process there, they are the same. It's just interchangeable in that sense there, right? And then due to error introduced by the equipment, right? An error due to introduced equipment there, measurement system there have these two components. And this called, this term we use, okay? All right. Now, so repeatability is also known as equipment variations, EV, or appraisal. This one reproducibility, appraisal variations, AV. This is using the AIAG there, the term, right? But common in statistics, those are things that we call repeatability or reproducibility. And important thing then is that next thing, like our process capability. We always want a single number to tell us what it is, what the things you want to study, and we can use a single number as a common language for benchmarking, right? So in the equipment for that, we have two scenarios. One is that we are concerned about the product spec. Product spec. Product spec are specifications given by designer, management, or customer, or by the process designer, whoever it is, right? So it's normally much bigger than the natural spec, correct? Product spec. So, the product tolerance, right? Product tolerance, specifications. The upper spec limit minus lower spec limit is a tolerance, right? So we always want to say that, okay, we want to compare that when you use equipment, based on the equipment you have, the measurement equipment error with respect to the specification tolerance that is how comfortable are we? That's one scenario, right? Because we are concerned about customer when ship the product out, we have enough margin we can meet. We don't introduce additional error so that we say this is good, and then when the customer say, this is bad, right? Those are things there, and that we can use it. But more importantly, is that we know that our process has natural process spread, plus minus 3 sigma of the process, right? Or the product, when you go in the manufacturing process, fluctuate, and then over a long term there, see, this is what the spread we have, right? And that thus our equipment, when you introduce measure, look at the value there, compare with the product, right, natural spread, what's the proportion? What is the error percentage introduced? Just our linearity, right? You see, if the linearity exercise we have there, see, is 13% of the measurement. It's quite army, quite big, right? If you want it to be less than 10%, right, all the time there, just a ruler, you want a 10 division instead of 4 division in 1 inch, right? The higher the resolution, the better it is, right? So you want to have discrimination, able to discriminate on the area that you want, interested. I can discriminate the measurement into how many categories of products, right? So that the product, you say, is a long bar and a short bar within the specifications, and that how big the difference between long and short bar. And my measurement equipment, you see, introduce how much error inside there. If my measurement equipment treat 30% error there, wow, I can measure something not so good, right? Because when I say that I measure a 20 millimeter length, right, for instance, if my equipment, say, let's say, for convenience sake, introduce 5 millimeter error there. So when you measure 90 millimeter on a bar there, if my equipment can introduce 5 millimeter error there, are you sure that your bar is longer than 5 millimeter or far shorter than, the far shorter than 90 millimeter? That kind of error, you cannot live with that, right? Because when you say, I measure 90 millimeter, I want to actually show there's 90 millimeter, so that I would cross over 20 millimeter when customer take an out ruler measure that, hey, your bar coming in is 23 millimeter, right? So you don't want that scenario, right? So in that case then, is that, so we have two method, two ratio, like CP, CPK, CPU, CPL, right? So in equal measures, we have two. One is for relevant to this tolerance one. The other one is total variations, right? So in this case here, the general is called precision to tolerance is P/T ratio. The equation is K times this sigma R and R. What is R and R? Repeatability and reproducibility, right? Due to standard deviation due to that, right? And divided by their tolerance. Right? The K is our control chart. Control chart, our K is always, we tend to use 3, right? Some European, we want to use it, 3.09 or something there, right? So in this case here, right, K can be 5.15 or 6. When it's 6, what do you mean? Right, remember we have this thing here. Right. If it's natural variations, we have minus 3 sigma, this is plus 3 sigma, right? So it's plus minus 3 sigma there, K equals 6. Right. When K is 2.515, what does it mean? Divided by 2, right? It's 2.575, right? So it's 2.58. 2.58, what it is? 2.58, what it is? You remember your standard deviation table? To the 2.58, right? 995, right? So this symmetry, right, 99%, right? Okay? So you see that this habit die hard. People want to use the 99% one, right? Things that in the car industry, legacy from all the way to UK, European, go to US, when they make all the gun, and then after they make cars, those are things there, and sometimes they stick at 99%, right? So a lot of times there, until 60s, 70s, till 80s, when I was in 60 Mountain and then 80, 90 around there, I talked to those GM and then Ford guy, right? I know a lot of them say, oh, 99% or something. But then lately, they switch over to 3. As I said earlier, people are more receptive to 3. So when you use this number, PT, you need to specify which K are you using. So that because 5.5 and 6 multiply makes slight difference. Okay? Typically, people use 6 this day, but there are still people using traditional legacy 165.5. Right? Okay? So this is 99%. This is 99.73%. Right? Okay? So this is basically saying that, how much error due to the repeatability and reproducibility with relationship to tolerance. Now, if you want to look at process side there, remember our total is equal to our product that you want to measure plus this guy here, right? So you square root of that, you get this total, right? So it's just a ratio of this thing over this thing. So you say, okay, your repeatability and reproducibility, how much is over on the total measurement range that you want to have? Measure total variations in the process that you want to control. Right? So as I say there, see, if the error is, is 5 millimeter, and you are at 19, you observe 19 millimeter, and your requirement is 20 millimeter max. The error will basically, make you look stupid later on, right? If the equipment is so bad. So, rule of thumb, your PT or GRR, percentage there, right? If it's less than 0.1, that means that, let's say 1 inch, right? It's 0.1 division there, see? You have 10 resolutions, right? 10 inch, 1 inch there, right? So this is acceptable, reasonably good. But then in modern days, especially when measure length or something, you can use laser to measure already. Last time you have used micrometer, vernier caliper, or something to measure. It sounds today's technology is very stupid. And when I calibrate my CNC machine or something, I use laser beam to measure it. I can go to micron, But then the stupid machine vibrations, they shake it out, see? More than that, right? So especially those guys in the wafer there, right? If someone walk behind there, just stumble, the number will just jump over the place, right? Laser is so good, right? Interferometer, that kind of things there. So if you have resolutions, PT is 0.1 or 10%, I think you're okay, right? 0.1 or less, and it's 0.3 or more, basically it is not acceptable, right? And that because, let's say the 1 inch, just imagine, earlier we say you have 10 divisions. 10 divisions, 1 inch, you can quite fine, right? The resolution is, you have 20 divisions, of course, so much better, right? So, but then, if it's 1 inch, you have only 3 divisions. It's no good, and you have a lot of guesstimate, so that is no good, right? Suppose it's between these two numbers. Depends on the situation. Preferably you do what? Because your resolution is not good enough. Your discrimination is not good enough. And whatever you measure there, you can have false reject or false accept. you know, you reject one, suppose reject, but then you may make a mistake to accept it. So it may introduce error. And then just imagine in your work area there, if you have the inspection station there, use the equipment like this to measure. Sometimes you say it's reject, sometimes you say it's accept. If you say reject, you got to rework, it's scrap. Or you double check again, you're wasting resources. So this is a compromise. A lot of times you don't want to have a compromise. See? If you have no money problems, right, you don't want to have a compromise because scrap or reject is a pain. It's a waste of resources. But if you reject one, you accept, and then ship it out, customer reject, it's also bigger pain, right? So you want to avoid those sort of things there. So by right then, you should reject them, trade off, right? So it's a trade off between cost, right, and all sort of stuff there. By right, you don't want it, huh? Okay. So now, so this is what we have, right? So you know the basis things that like CP, CPL, CPU, CPK. In the measuring equipment there, we have two parameters, PT ratio or GRR. Right? PT ratio, GRR. So now, how are we going to do the GRR? Right? So I'll set the motion going on this part here. And that, so I'll give you an example first, right? And that, but first thing, we'll revisit this one, slightly later, right? How you want to get the standard part. I think some of you are involved with doing measurement equipment analysis, right? Some of you may, you all don't want to say only, some of you may not, but some of them are equipment manufacturers. Some of you also do something on that one, right? So probably, let me explain the underlying principle first, right? Okay. So my recommendation in this case is just grab it first, right? Whatever you do there, take 10 to 20 parts that is actual in the expected range, right? You randomly select, right? Take one maybe in a day, spreading over several days, so that you have a shorter and a bit long-term process when you get a sample, right? So it's like a natural variations. So that you get a little short-term, a little bit long-term, mid-term or something like that, so you get it up, you get the whole picture on that, right? You get a sample, randomly selected, right? Over the range there, right? Then what you do is that to study this thing here, let's say that your first appraiser, you get 10 to 20 parts, right? Typically what you do is that you label them, 1, 2, 3, 4, 5, 6, and then you and a separate master sheet there, you know 1, 2, 3, 4, 5, 6, what are the true value, right? Those are things. Or you don't know, you label them, you know what it is there, right? Just let's say that you know which are the sample. So what you do is that you get first use your equipment, you get the first appraiser, and then randomly sample 1, sample 2, and then randomly throw to them. You don't go a sequence, right, or something. It's just random. Because human is very funny. If I give you this thing, I keep measuring this thing here, right? After the first 2 readings, the third reading, when I use the equipment to measure, I project it, you know. What is the reading? So when you try to project it, you're biased already. You try to guess it, right? You measure it multiple times. If you measure it repeatedly same time, all the time there, you try to guess it already. You say, hey, it's in between this tick there, earlier I said it's 0.5, I do it 0.4, then now I see come back again, so maybe a 0.4, 0.45 something, instead of 0.7 or something randomly, right? Do it there. So you need to be random, right? You take part, right? You randomly give them measure, first appraiser, then second appraiser, right? Measure once, random order, and then you want to measure again, right? This is trial 1, right? Then you repeat the step again, second trial, right? Then after that, we do the HR and R study by using the XRR chart. right? Typically, the most important thing is the R chart, right? And I will explain it why. Then after that, we go to calculate the repeatability, reproducibility, and the product variation, and then total, right? Subsequently, we get the total. And then we calculate the PT ratio or the GRR number. Then we look at the result, and then compare whether are these the range that we want, and then see whether they accept it or not. Okay? Right. So we take this example. Now, this example, very simple. I just let you go in first, sink in first, right? This is the example that we have only one appraiser, so we don't have second appraiser. Right? We have 20 parts, right? 20 parts, and that we have 20 parts, but each part we measure 2 times. Right? I tabulate in this way so that this is the result, but then this way we want to do it is that we want to randomly throw the number there, and then sample there, and then get the people to measure it. Right? Measure 1 time, and then throw a random number again second time, measure the second time. So after that, then you tabulate this one, right? So when you tabulate this one, you can get the average reading, and then the range, right? So you tabulate it, subsequently you get it. The whole grand mean is 22.3, and then the range R, right, is 1. Okay? So if you look at that, this is like our control chart. Our control chart, we have 20 samples, and the sample size, what is sample size? 2, right? So when you have 2, you are using S bar R chart. So what is a D2? You go to check out your D2, right? Okay? And D4, those are things there, right? So let's say this one, right? So you can get this one, right, from chart. So n equal to 2, right? So our D4 is 3.27, and D2 is 1.28. And remember, what is the D2 used for? Remember? Remember that our estimator is equal to this one over D2, right? And then for our X bar R chart, right? We can A2, we need this for the X bar, right? And then we need D3, D4 for the R chart, right? Remember the upper control limit, lower control limit, that kind of stuff there. So we have this thing here, right? Remember the first step we want to do, right? Is that what you have, right? So in this case, we have only one appraiser. So reproducibility is not there. We have only repeatability. And repeatability, because we have every sample you take 2 times. So we can say, hey, you should be consistent all the time, but then in real life it's not, right? So we have variation. So if this is the case, then we have it, right? So I just plug the number since you all know you all done the work already, right? So we have this part spec is upper spec is lower spec, this one. So the tolerance is 55, upper spec minus lower spec. So you plug in all the value that we have, right? So the A2, this one, upper control limit is this guy, and then lower control limit this one, right? And then you have an R chart, D4 is 3.327. The lower limit, D3 is always 0, right? N less than 7, right? Okay? So our upper control limit is this one, the range, the mean value, right, is 1. So you have an R chart, is 1. And then lower control limit is equal to 0. Upper control limit is 3.27. 3.267, right? From this part here. So 3.267, you look at this chart here, this part here. Is that our control? No, right? Then we come to this one, later on, right? So then, you know that from your D2, right, your R is 1, and then divide that, this thing here. So if you use 5.15, K equal 1.5 right? You can use K equal 6 as well, Okay, So your PT ratio is, this one is equal to, right, 4.083. So 0.083 is good or bad? Acceptable or not acceptable? Good, Okay, acceptable, right? So looking at that, you got a few already, right? But we don't have the reproducibility yet. This is just the repeatability on it because you have only one appraiser using the same sample measuring twice, right? So you have only a variation due to repeatability, right? Now, so this one is what I have plotted out in the X bar R chart using Minitab, Okay? Now, so this one, this is our R chart. So it looks okay, right? I mean, the Minitab flagged it out something there, because it checked the Western electric rules or something there. And the fact that this guy flagged it out here, see, is that because what is this? 8 out of 9 on one side. There's something there, but to us this is not a trend because this is the range we have, right? So don't worry. As long as it doesn't hit the upper limit or the lower limit, then the range is okay. By right, we want the range as narrow as possible, right? Okay? Now, for a measuring equipment, using measuring the same part, if your equipment is good, what do you want the range, expect the range to be? Ideal. 0, right? Ideally it would be 0, right? Very repeatable, and then you have no variation. The variation is 0, right? Ideal one. Life is not ideal, so you don't have it, right? Okay? But then you see, if you start to see in the range chart, point that's outside the upper control limit. Because we have a lower limit is 0, so you don't want that, right? It's always narrow to 0, so, but you think that's outside the upper, hit it or near to the upper control, you swing upper and lower control limit, very, very wildly one, see? When you look at R chart, what does it tell you? What does it tell you? One moment you measure the range is 0, one moment you measure the range is maximum swing. That means that the operator or the equipment may have some difficulty in using it because the range is always swinging out or something like that, right? Maybe when I measure it, this guy had a dirt there or something like that. So if you have that kind of weird scenario, not something randomly in between the upper and lower control limit, but some weird scenario is swing either to extreme there or outside the upper control limit or something there. Something weird is happening. And you should check that out. Either the guy have problems of using the equipment, or the equipment itself is not very repeatable, it's very wildly swing, or they have dirt, or some get stopped, worn out, or something, your component there, you see, you place it there, it's not right, or something like that, right? Or sometimes if it's analog time, you get problems of reading the needle. Sometimes needle stuck or whatever it is there. Can happen, right? So preferably you always want the digital, so you dial it out on all the human parallax error, right? Okay? So you check that, right? And for any measurements to be valid, equipment analysis there, the range chart must be in control. Right? That's why I put it in the first statement in the first slide there, in control, right? Then let's look at X bar R chart. Wow, you say that, oh, all these guys are out of control, you know? Out of control, you know, so many. What happened? Now, you think about our analogy, right? If your equipment is good, repeatability should be, the sigma there, right, should be near the zero or zero. So if near the zero there, right, your reading should be always consistently around the midpoint there, never bump out and down there. And then when it's near the zero there, see, what is upper control limit and lower control limit? Very tight, right? R is small, then it should be very tight, right? So, and this is the purpose you want it for the X bar chart. Because you want to discriminate the part that's over the whole range of production that you're going to have to spread, right? And you should be bouncing out X bar there, see, for good equipment, which all should be out of control. But the R chart must be in control to be meaningful. Get the point? Make sense? Then you can discriminate on the process. There's intention. That's why, see, the more out of control in the X bar there, see, the better it is. Right? So that is the intention, right? By right, this one should be very tight. For very good equipment, resolutions of better than 10, like 0.1 and smaller than 0.1. The PT ratio or GRR ratio. So it should be very tight on that, right? Okay, so we spend 1 hour on this one, doesn't matter, huh? That's what I want to communicate to you all, right? Okay? Now, second thing, give you a few more minutes, then we talk. We say this, then we go and break, right? This is very important now. We go to the second part of that. Just now we say we only have repeatability. Now, it's the same example. I introduce you 2 more additional appraiser, or inspector, or engineer, or operator, doesn't matter. Huh? You know what is on that, right? So now we have more people measuring the same sample using the same equipment. Now we introduce a term called reproducibility inside. Right? So this is the chief of that. Okay? And that in actual case, right? This technique coming out later on publicized by AIAG, the Automotive Industry Action Groups. They published a series of manuals to standardize the measurement because they have a lot of people doing in the industry. So they standardize it, and that, so what we have is that the simplest method they do is that to do GI, MSA, they call it GI and R as well, study measure. The whole thing is they include more things, right? Range method, X bar R method, right? So range method is just like what we said earlier, and X bar method as well, right? Depends on how many measurements you have, right? So this is more elaborate on that, right? And there's another method called ANOVA method. This is called analysis of variance, right? And this analysis of variance, I'm not covering here. What we do in the Minitab there, Minitab give you all the methods available. Okay? And the reason that I'm not covering here analysis of variance here, right, is very computational intensive. If you want to have a little feel of this, I give you that. You can refer to your page Montgomery 148 to 152. And see what this, maybe I just click over. And you need computer to do it, right? So this is in a sample 7. Okay. Okay. So it's basically involve a model, y equal to the mean value plus certain factor, and then this is the error term. So if we have a more factor, like our factor is that we have parts factor, we have operator factor, right? We have equipment factor, or sometimes there's other factor inside there. So this term increase different, you introduce more term inside there, right? And then what you cover is that they typically they want to collect this number of terms and then number of observations, and then you do a lot of computation. The computations is very yucky one. A lot of these summations and this, you know, and more. Multiple summations mean it's like you want to study the variance, and then you want to have minimum, maximum likelihood, minimum least square, those are things there, right? So you get all the square terms, sum it out, and subsequently want to dial up what is average, mean, variation, something like that. So subsequently then you go to classify it under associate with different factor, and then you calculate what is the factor contributions to the variations. Right? So it ends up, you get a mean square term and a lot of this yucky term. You need computer to calculate it. It's no way you want to do manually. Okay? I just let you have a few because every time I mention it, and then I'll say, what it is there, you know, why you don't teach us a relevant thing. So you can pick it up, your job requirement, you can pick it up using a Minitab or something like that, do all that. But I just let you know that you have this thing here, right? So AIAG there, they have this thing, but then typically, if you use the AIG template there, you use this method because you can calculate by hand or calculator, right? Because X bar R, remember X R bar, very simple, right? ANOVA, you need computer, right? Okay. And then in the Minitab, they got a lot of different type. I just touch base on that. It doesn't mean to, you know, frighten you, those are things there, right? And you got a gauge study tab inside there under the stat quality tool, right? Gauge study. Under there, you have this type 1 gauge study and then gauge R&R study. Let me show you that. Okay. I just introduce. So you go to stat, quality tool, you got this gauge here, right? So you have type 1, and then you have this, when you want to do a study, they can even generate the table for you, worksheet for you, such that you randomize your sample, right? And then you have these three things here, right? Gauge study, cross, nested, expanded, right? Then you have attribute, we'll talk about attribute later on, right? So, not to worry, okay? So, what I basically want to talk to you then is that cross is the one that typically we use. This one gauge, type 1 gauge there, see, is for people to, you have one sample, you want to have a quick check on your equipment there and say, how bad is your bias and then repeatability. You measure multiple times, then after that, from there you calculate, what is your, just an chart, just down the one a little bit. So, not much use one. So typically you use this one here. I spot the example we are going to do, right? Nested is for destructive testing. You get a sample. Your sample, when you test it by minimum tensile strength of a bar, right? You test it, when you test it, the sample is gone red. You can use the same sample to measure the second time. So you have to make some assumptions that the batch is something is consistent. You take one sample from there and then take a second sample, it's the same thing, so you can do a second reading or something. So it's a bit unique situations for that, right? Expanded is the one that is a little bit more flexible, it's general terms, but you need a lot of readings. And that basically is something like, first operator measure 10 sample, and then somehow when the second operator comes, he has only 5 samples to read, right? And then you have this unique different set of number there, and how you handle these things there. So it gives a more more complicated scenario equations to do this sort of thing. And all these are based on ANOVA, right? And the cross one, you can have X bar or ANOVA inside the Minitab. Let me show you a little bit, show you some example here. Let's just, right, before I give you a break. Right, so you can have this thing here, and then subsequently you have they give you, right, ANOVA or X bar R. So in our case here, you want to do the calculations, we use an X bar R, right? Okay, because then you can calculate out very fast. ANOVA, you need computation, as I showed you earlier, right? But if you have Minitab, you want real job, you can do it, you can use ANOVA, it gives you a little more angle to look at a little bit. Right? I will touch base on this later on. Okay? So now in this case here, right, typically when we have this type of scenario, we have average, we can range, so we can get the mean for the first operator and then the range, right, for the first one. Second one, we can also get this same thing, right? Third one, we can also get same thing. Now, because this thing here, we have three operator, and we want to look at the product, since we have so many 20 parts of it, we measure so many times, right? We can also, if these 20 parts are representative of process variation, you say that as I take a look at it in a sense that day 1, day 2, day 3, day 4, you spread it over a few days to take it. So you have a lot of short-term, cumulative to the mid-term, not so long-term data, right? So it should be quite a natural big process variation there, see? So we say that, okay, the part there, see, overall you take the average, this one here, this guy here, and this guy here, right? Or you can take this one, plus this one, plus this one, you know, and then you take the average, grand average of this part here, part average, right, for all the three operators. Then you can do it all, and then you say that this minimum value inside here, 18.2, right, is somewhere, where is it? 18.2 minimum. This one is minimum, right? Maximum is 29.7. 29.7. This is the maximum, right? Sorry, 29, right? Huh?
Yeah.
Below, right? Somewhere you see that. Yeah. Okay, so you know that, right? So when you see this thing here, R, and these are things here, right? You think that likely we are going to use some things. Right? So this is why the control chart is very important. If you want to use these things, then remember we have this thing here. That kind of stuff, right? And this one will help us to find out what is the variations in there. So we'll talk about it after our break. That's 40 lah. 1940, we come back. Then we continue. Okay?